Section 2.5, the limit laws. We have two objectives here. One, apply the basic laws of limits, and two, evaluate limits analytically, meaning algebraically. In the previous section, we focused on finding limits numerically and graphically. We use tables and graphs to find the limits, but in this section, we will focus on the third method or the third approach, which is the analytical approach. This is the only one that gives us certainty when we're solving limit problems. And right off the bat, we have a theorem with multiple parts that I recommend that you save in your notes. So take a screenshot of it or pause the video and copy it down. And I'll be referencing it multiple times in the next few problems, but later on we will be so familiar and so comfortable with using limits that we won't have to reference the theorem anymore. We'll just be able to do the problems right off the bat. But I just want to point a couple of different parts in this theorem for our use later on. For example, this one right here, number 2, basically tells us that the limit as x approaches a of x is just simply a. So if I'm approaching a and I'm just evaluating the limit of x, then the answer is just going to be directly a. The other one I want to point out is the following one, which is the limit as x approaches a of some random number k, and we're told that the answer is equal to k, where k is a real number. So if I'm approaching any random number, x is approaching any random number, and I'm taking the limit of a constant, the answer is the same constant I began with. So let's use these two rules and the other ones in the next few parts. So in example 1, it's telling us to find or evaluate each limit. So evaluate or find, it's the same. And basically the goal is to find the limit of 2x as x approaches 3. Now sometimes some parentheses will be written, some parentheses will not. I'm going to put the parentheses around the 2x so that I can emphasize that I'm evaluating the limit of the function 2x with x approaching 3. Now if I look at my theorems above, one of the theorems tells me the following. It tells me that if I have a limit of a constant times some random x's, I can ignore the constant and pull it out of the limits. So what does that mean? For me, that means this. I have a 2x in here, and the rule number 3 allows me to remove the 2 from the expression and put it in front of the limit and have 2 with the limit x approaching 3 of x. So this rule allows me to take the constant out and ignore it basically. It's being multiplied with x, so I just put it on the front with the multiplication sign next to it. I'm writing the 3 on top of the equal sign so you can remember which rule I used to modify this expression. And again, the rule is the one where you're allowed to pull the constant out. Now, earlier we referenced another theorem, and the theorem was that if you have the limit of x, regardless of what x is approaching, the answer is the variable or the constant a. So the limit of x as x approaches a is equal to a. And that's exactly what I have in my theorem, or my problem rather. The limit as x approaches 3 of x. So this I'm allowed to rewrite using rule number 2 as just simply 3, because that's the number that my x is approaching. So I just write that number down. And obviously I'm going to write everything else 2 times and the 3 that we get from the theorem. And we used rule number 2 or part number 2 of that theorem. So let's just write 2. And finally 2 times 3, we don't need any rules for that. This is just equal to 6, and we are finished with part 1 of this example. So now that we're done with that, you can kind of see what the process is going to look like. And let's do the next few parts, referencing all the details. So the next one we have to do is the limit as x approaches 3 of 5 minus 2x. So the critical thing to remember here is that I have a minus sign, so I'm going to look at my notes, and there is a rule that tells me what to do when I have a plus or minus. Basically, the rule says if you have a limit of a sum or difference, you can take the limit of each of the parts and then add or subtract as needed. So in my case, I have a limit of 5 minus 2x. So what that rule allows me to do is it allows me to do the following. Write the limit as x approaches 3 of 5, and then the limit as x approaches 3 of 2x. And I can put a minus in the middle because when I began the problem, I already had a minus sign. So that's what rule number 4 lets me do. So you remember, I'll put the 4 over here on top of the equal sign. Now, as we mentioned before, the limit as x approaches 3 of some random constant, that is the constant itself, the 5, right? So that's, what rule is that? That's rule number 1, right? The limit of a constant, regardless of what x is approaching, is the constant itself. So that means I can remove limit x approaching 3 of 5 and just write down 5 using rule number 1. And I'll put the minus sign as we had before. And now I need to find the limit as x approaches 3 of 2x. But thankfully, we already know the answer to this. We just found it previously. It was in part 1 of the problem. We know that that whole thing is equal to 6. So this is by part 1 of example number 1. So I know that that should be 6, and now 5 minus 6 is -1, and I am completely done with this problem. So as you can see, we'll basically be modifying the given problem, breaking it into parts using the rules in the table, and as we bring them into smaller and smaller chunks, we will be able to evaluate each chunk individually. Okay, so next we have the limit as x approaches 3 of x plus 1 divided by 2x. And I just want to pause for a second and say there's nothing sacred about x approaching 3. I mean, it just happened that I picked all the first 3 parts with the same x approaching 3 for all of them, but that's not very usual. Typically, you'll have random numbers, and you'll see in the next problem we have a different value. But anyway, for this one, I'm going to start by writing the problem down. Limit as x approaches 3 of x plus 1 divided by 2x. Okay, so first of all, I have a theorem, which is rule number 6, that tells me that I can take the fraction of the limits. So the limit of a fraction is basically the quotient of the limit. So it allows me to take a limit and put it on the numerator, and a limit put it on the denominator, and write limit of x plus 1 divided by limit of 2x. So this is rule number 6 that we are provided with in the table. Now for the numerator, I have a limit of x plus 1, and again, using the same theorem, but a different part of the theorem, actually part number 4, I can break the limit on the numerator into 2 different limits. So I have a sum of x and 1, so I can write it as a limit with x approaching 3 of just x, and then limit as x approaches 3 of 1, and then put the plus sign that used to be there in the middle between these two guys. And the denominator, I'm not going to worry about it because we already know from part 1 the answer is equal to 6. So I'm just going to write 6 right away. And I'm not going to explain how I got the 6. If you want to know how, just re-watch the first part of this video. Now, we're almost finished here because all we have to do is now find the limits of x as x approaches 3. And we kind of mentioned how to do this. Rule number 2, or part number 2 of the rule, tells me that this should be just simply x. 3. And then I have the plus sign, the limit as x approaches 3 of 1. The 1 is a constant, so I'm allowed to say that the limit as x approaches 3 of 1 is equal to 1, and the whole thing is divided by 6. And so this is 4 over 6, which can be reduced if we divide by 2. On the numerator and denominator, I get 2/3, and that's the final answer for that portion of the problem. So as you can see, it's not too bad. So let's continue with the next part. The next part has a slightly more complicated expression with limit x squared minus 5x plus 6, all divided by x minus 3. And so the limit is approaching 1. So let's begin by writing down limit as x approaches 1. And we will give the numerator 5x plus 6. And we will have the denominator x minus 3. We will give each one of those its own individual limit. So first I'll write a fraction, a really big one, and then I'll put the limit as x approaches 1, and then I'll have x squared minus 5x plus 6, that's the numerator. Then I'll give a limit to the denominator part, which is x minus 3. And once I've done that, that's using rule number 6, by the way, if you are keeping track or keeping record. This is rule number 6. The limit of a fraction is the fraction of the limits. Then I can now use my other rules to break this even further. So for instance, on the numerator, I have a minus and a plus. So each one of those can be broken down. So we can have a limit as x approaches 1 of x squared all by itself. And then we can write the limit as x approaches 1 of 5x. And then we can write the plus limit as x approaches 1 of 6. And it's now going to be divided by the limit of x minus 3. Again, I have a minus sign in here. So again, I can give each one of the different factors its own limit. So I can do limit of x as x approaches 1 minus limit of 3 as x approaches 1. Okay, and which rule allows me to break these apart? Well, that's rule number 4, which says if you have a plus or minus, you can just ignore it and give the limit to each one of the factors. Now, using rule number 7, I'm going to focus on this first limit, and it says I have limit of x squared. According to rule number 7, I can just take the square and put it on the outside of the whole thing. So actually, I can write basically the limit as x approaches 1 of x and give that whole thing the square instead of giving it just simply to the x. So everybody gets the square, not just the x, and I don't have to write the x squared inside anymore. I could just write simply x. Next, I can move the 5 from within the limit. So instead of having a limit of 5x, I can have 5 limit as x approaching 1 of x. And finally, there's nothing to do on that last one. We will write limit as x approaches 1 of just 6. And same thing with the denominator. There's nothing to do there, so we will just write all the different parts just for the record. Okay, so here I used basically two rules. First, to bring this 2 out, I used rule number 7. And then to bring the 5 out of the limit, I used rule number 3. So 2 rules were used on that line. And now we are basically pretty much done. All we have to do is find the limit of x's or the limit of the constants. So let's begin with the first one, the limit of x as x approaches 1. That just is equal to 1, and the 1 was squared previously, so we'll keep it squared. Then we have 5 times. Next, we have the limit as x approaches 1 of x, and that's just going to be simply 1. And finally, we have the plus limit as x approaches 1 of 6. That's going to be just simply equal to 6. So that third one is the limit of a constant, and it's the same as the constant. Now, moving on to the denominator, I've got the limit as x approaches 1 of x. And again, using rule number 2, the limit is going to be 1 there. And finally, the limit as x approaches 1 of 3. This is the limit of a constant. The answer is just the constant itself, which in this case is equal to 3. So which rules did I use here? I used a combination of rule number 2 for all the terms that have an x and rule number 1 for all the terms that have a limit of a constant. And so now we can just use our PEMDAS to figure out the answer to this thing. Turns out that my answer is -1 in this particular problem. Now what I'd like to do before continuing further is to repeat this problem and show you what the shortcuts will basically tell us to do. So I'm going to rewrite the same problem, the limit as x approaches 1 of x squared minus 5x plus 6, all divided by x minus 3. And what I want you to do from now on, and you can do this for the previous problems that we just finished doing, is this. I want you to just take this x down here, which in this case x is approaching 1, and I want you to just plug 1 into the expression and see what happens. Let's just test it out. So we're just going to grab the 1 that x is approaching to, and we will replace all the x's with 1, and voila, that's basically how it's going to look, right, with all the x's being replaced with 1. And I don't know if you noticed, but this right here is exactly the same outcome that we got previously when we wrote out and spelled all the different theorems that allow us to manipulate. And obviously, we can now continue. PEMDAS says square root of 1, so I'm going to have 1. 5 times 1 is going to be 5, plus 6. All divided by 1 minus 3 is going to be -2. And 1 minus 5 is going to be -4, plus 6 is going to be 2. All divided by -2, which is -1 again. So it seems like plugging in the number is actually faster than using the theorem. And this is okay as long as you don't get a 0 on the denominator. If you get a 0 on the denominator, then this plug-in the number won't work and you'll have to use some other method. And that's what we're going to be basically demonstrating in the next few pages. So if you want, we can go back and revisit the previous one. So if I use the shortcut here, this is the limit as x approaches 3 of x plus 1 divided by 2x. And so according to my shortcut, all I got to do is take the x is approaching 3, put 3 into all the x's, and we'll see what happens. So I get 3 plus 1 divided by 2 times 3, which is 4 over 6, which we already said is 2/3. So you can see that the answer that we're getting is exactly the same one that we previously had. And that's the beauty of this little shortcut, is that even if you don't know any of the theorem's numbers, you can use it and you can get the right answer. And this works as long as your denominator does not turn out to be 0, in which case you'll have to do some different algebra to try to avoid the 0 on the denominator. So this last method that I just showed you that involves plugging in the number is called the substitution method. So it works really nicely when you have polynomials on the numerator and the denominator. Even when you don't, certain times it still works. But if you end up having 0 on the denominator, then you'll have to use some kind of algebraic technique to try to avoid the issue. So let's see what I'm talking about with example number 2. So in this case, I'm given a limit with x approaching 3, and we have x squared minus 5x plus 6, all divided by x minus 3. So if I want to use my shortcut, I see that x is approaching 3, so I plug in 3 into all the x's, and what do I get out of this? Well, let's see. I get 3 squared, which is 9, 5 times 3 is going to be 15, plus 6, all divided by 3 minus 3, and I don't need to kind of work it out. You probably already know that this is going to be 0 over 0, which is known in math as an indeterminate form. So whenever you have 0 over 0, that's called an indeterminate form. And if you end up with that, then unfortunately, that means you have a little bit more work to do. So depending on the problem, when you have 0 over 0, you may have to factor and reduce, or you may have to multiply by the conjugate, or if you have like complex fractions, you may want to like simplify the problem. In this case, I'm dealing with a polynomial divided by a polynomial. So what I have to do is redo the problem, but before I can use the substitution method and plug everything in, I should try to factor the expression on the numerator and the denominator if possible, reduce it to lowest terms. So in this case, I have the limit as x approaches 3, and we have a numerator with a quadratic, x squared minus 5x plus 6. Maybe we can factor it. So let's see. I want two numbers that multiply to basically 6. I'm looking for two numbers multiplied to 6, but when I add them, I get negative 5. So think about this problem for a second. Can you find two numbers that when you multiply you get 6, but when you add you get negative 5? Well, I'm thinking negative 2 and negative 3 might get the job done, because negative 2 times negative 3 will be 6. And when I combine negative 2 and negative 3, I get negative 5. So great. I can now rewrite the numerator as x minus 2 and x minus 3 instead. So I can turn the original x squared minus 5x plus 6, which was a quadratic, into a product of two factors. Now, thankfully, the denominator here is x minus 3. I don't have to do anything for that. It's already as factored as it will be. And notice how I'm seeing now that there's an x minus 3 on the numerator and another x minus 3 repeating on the denominator. So what we'll do is we will reduce it to lowest terms. So we will divide them out. And when you divide them, they just become a 1. So they don't disappear completely. They turn into 1s. So now I'm going to have the limit as x approaches 3 of the fraction x minus 2 with denominator 1. And so that's it. There's nothing else to reduce. So I can stop now. And I can say, well, wait a second. X was approaching 3. How about I try the substitution method again? How about I put it there? So if I do, I get 3 minus 2 over 1, which is 1 over 1, which is exactly equal to 1. So that means in this particular instant that the 0 over 0 was able to be removed in the problem, and my limit turned out to be equal to 1 eventually. So this is our first method, or our first look at what to do when we have an indeterminate form with 0 over 0. We will see different scenarios as we go to the next problem. So in the next problem, we have fraction, but we have radicals on the numerator, and we will have some other problem down here with fractions, with fractions within fractions, so complex fractions. And for each one of those different problems, we will use a different strategy. So let's begin with example 3, which says to find the limit as x approaches 0 of the square root of x plus 2 minus square root of 2, all divided by x. And right off the bat, I'm seeing x approaching 0. So we will always try this first. We will plug 0 in all the places where we see x. And this is all allowed by the theorem that we saw at the start of the section, by the way. I'm just not specifying which part of the theorem I'm using. And so if I did this, if I removed all the x's and replaced them with 0, I'm going to end up with the square root of 0 plus 2, which is square root of 2, minus square root of 2, all divided by 0, which is 0 over 0. And I don't need to tell you anymore, this is an indeterminate form, right? So indeterminate form means you're not done with the problem. It means that there's an answer. You just have to work harder for finding it. You just have to do some kind of manipulation algebraically to remove the 0 over 0 from the problem. And in this case, I'm seeing radicals. So the process is going to be multiplied by the conjugate. So we will redo the problem and we will start by writing it down, and then we will write it the second time. So the limit as x approaches 0, and we will write the square root of x plus 2 minus the square root of 2, all divided by x. But this time, the way to fix it is to multiply it by the conjugate, and in this case, the conjugate is the conjugate of the numerator because that's where we can find the radicals. The conjugate is going to be x plus 2 with the radical plus the square root of 2. And whatever you do on the numerator, you have to do exactly the same process on the denominator. You have to multiply by the same exact quantity. So we'll be multiplying the numerators with each other, and we'll be multiplying the denominators with each other. But in fact, I'm not going to FOIL the denominator. I'm just going to FOIL the numerators. And in this particular problem, when I multiply the numerators, this has the pattern A, B. This is the same A. This is the same B with the plus and a minus. So when you multiply A plus B and A minus B, the answer is clear. It's supposed to be A squared. So the x plus 2 must get squared. And minus the B squared, meaning the square root of 2 must be squared as well. And like I said, on the denominator, we won't actually FOIL or distribute anything. We will just leave it like it is for a few seconds, because ultimately what happens in these problems is things end up reducing. So the factors on the numerator and denominator will appear, and we will be able to remove them. And by the way, the square root and the square will pretty much cancel out in this case. So I'm going to rewrite the problem without these radicals and squares. Now be careful if you have multiple terms in the second parentheses, you will need to keep parentheses around it. In this case, I only have a 2, so I don't need to write everything with parentheses everywhere. I could just ignore everything. But anyway, the 2 and the negative 2 on the numerator will cancel out because 2 minus 2 is going to be 0, and I'm left with just simply the limit as x approaches 0 of x on the numerator with x on the denominator, and the product is going to be x times the square root of x plus 2 plus the square root of 2 on the denominator. And finally, again, I'm seeing an x here and an x there. The x on the denominator is being multiplied with the parentheses. So we can remove these x's, divide them out. And when you divide them out, your answer is just going to be the limit as x approaches 0 of 1 divided by the square root of x plus 2 plus another square root of 2. And we are finished. We can't simplify it any further. So what I'll do now is I'll remember, well, let's try the substitution method. There's an x approaching 0 here. Let's plug it everywhere we see an x and see what happens. And if we do that, we end up with 1 over the square root of 0 plus 2 plus the square root of 2. 0 plus 2, by the way, is just simply 2. So this is 1 over 2 of the radical 2's, because we will have square root of 2 plus another square root of 2, and that's going to be 2 of them, basically, because we're adding the numbers on the outside. 1 plus 1 is going to be the 2 that I see over there. So my answer is now visible. It's 1 over 2 square root of 2. So in this particular problem, the 0 over 0 turned out to be eventually 1 over 2 square root of 2. Okay, now looking at example number 4, we have the limit as x approaches 4, and we will have some x's. So let's see what happens if we try the substitution method. So it's always recommended that you try the substitution method before you start thinking about, well, let's see some other option. So I'm going to first notice that x is approaching 4. And if x is approaching 4, let's see if I replace x's with 4, what do I get? Well, it's clear I get 1/4 minus 1/4 divided by 4 minus 4. So the numerator is going to be 0 and the denominator is going to be 0. And this is what we call an indeterminate form. I'm writing IND instead of the whole word, but that's what I mean when I write IND form. So it's the indeterminate form 0 over 0, which means there is an answer. It's just that I have to work a little bit hard to find the answer. And so again, what to do? In this case, I have a complex fraction because there are fractions on the numerator of the fraction that I'm dealing with. So the method is to simplify everything, clear it out, reduce it to lowest terms, then do the substitution method again. So we're going to start by redoing the problem. So we're going to redo the problem, and let's first write down what's given. And this is a good habit to always write what's given to you so that you don't forget or you don't accidentally start with the wrong thing or you don't drop a minus by accident. It's always a good idea to write down what's given. And so this time, what I'm going to do is I'm going to try to clear the fractions from my problem. And the way I'm going to do that is I'm going to multiply them all by a special quantity called the LCD. So I'm going to first pretend like this x minus 4 has a denominator, and it's 1. I'm going to look at this denominator, x, this denominator, 4, and this denominator, 1, and I'm going to ask myself, what's the LCD for all those? So although they're not on the same level, what's their LCD? Their LCD is 4x. So what I'm going to do next is basically multiply each fraction in my problem by 4x. So it's like I'm going to take this limit with the 1/4, the 1 over x, and I'm going to give it an extra 4x. Now, when I give it 4x, that 4x is obviously in the numerator. And same thing on the negative 1/4 that was already there. I'm going to give it 4x. And when I give it 4x, that's technically on the numerator. And similarly, the denominator already has x minus 4. And technically, there's an invisible 1 underneath it. And I'm going to multiply it with the 4x, which also has an invisible 1 underneath it. And when I do this, the idea is there shouldn't be any fractions. After I multiply everything out and reduce it to lowest terms, there should not be any fractions remaining. So let's see if that's true or not. So I'm going to write limit as x approaches 4. And we keep writing this limit until the point in time when we actually plug the 4 in. So you cannot drop it just because you're lazy or you don't feel like writing it. You should keep writing the limit until the step where you put the 4 into the x's. So that's part of the notation. Okay, so the first things first. We have the first fractions being multiplied. It's 1 over x multiplied with 4x over 1. Well, when you multiply fractions like this, you go straight across, top with top and bottom with bottom. But 4x times 1 is 4x and 1 times x is x. But then we can now remove the x's and we'll end up with just simply 4. So that's a 4. So the first fractions multiply with each other ended up giving us 4. And the scratch work is here off to the side so you can see what I did. In the same way, I'm going to treat these two fractions and their products, so I'll just do it on scratch paper. So it's 1/4 times 4x over 1. And you will go straight across, top with top. 4x times 1 is 4x, and bottom with bottom. 4 times 1 is going to be 4. And this time I can kind of cancel the 4s, and when I cancel them, they become 1s. And so 1 times x over 1 is just simply x. So the answer to the product was just x, and as you can see, there is no more fraction, which is what we're trying to accomplish. So we have 4 minus x, and then on the denominator we have x minus 4, all multiplied with 4x. And again, don't actually distribute, don't FOIL it, don't multiply it, just leave it alone for a second. Now let me rewrite this just so we can see what's going on. I don't like all the colors here, so I'm going to rewrite it with the limit as x approaches 4 with 4 minus x all divided by x minus 4. And you know what? This time I'll be writing the 4x in front because that's the more traditional way of writing down the product. Now, in an ideal world, I would like to cancel the 4 minus x with the x minus 4. They almost have the same letters and constants and variables, but the minuses and the plus situation is off. So what I'll do is I'll rewrite this top one as -1 times x minus 4 instead. And so check it out. We basically factored a -1, and when you factor the -1, you will have to flip the signs of the variable x and the 4. And if you want to test it out whether this is right or not, just FOIL it or distribute it in your head. Negative 1 times x will be the negative x that was already here, and negative 1 times the negative 4 will be the positive 4 that was already there. So by rewriting it in this factored form, I'll be able to reduce it with the x minus 4 that's on the denominator. So let me record that. So I'm going to write limit as x approaches 4, and then I'll be putting negative 1 times x minus 4 because I factored the negative 1. And down below we have 4x with x minus 4. And we're doing all this so we can now cancel the x minus 4s because now there's a product between them and everything else on the numerator and everything else on the denominator. So we're almost finished. This is now a limit with x approaching 4 of negative 1 divided by 4x. So we have to just worry about this part, negative 1 over 4x. And it can't be reduced any further. It can't be factored any further. So this is the time when I go, okay, my limit is x approaching 4. So how about I plug 4 there and see if I get an answer. As long as it's not 0 over 0, I'm happy. So in this case, I'm going to end up with negative 1 divided by 4 times 4. And this is going to be negative 1 over 16. And again, in this case, the 0 over 0 was able to be removed. And we ended up with negative 1 over 16 instead. So this is the third technique that you're going to be using. So you can either factor and reduce or remove the radicals by multiplying by some kind of conjugate, or use this method that relies on simplifying a complex fraction, making it into something more manageable, like what we got over here, and then reducing that further, and finally using the substitution method. Now I want to add that this method works even if my limit had x approaching 4 plus or 4 minus. Doesn't matter if these little powers were here. It doesn't have to be a straight up limit x approaching 4 every time. It could work if you have a 4 plus or 4 minus. That's what we're going to be demonstrating on this next page. So here we go. We have a function f of x, and it's a piecewise defined function. It's got 3 different names, and along with each name, the condition or the time when we can use that name. So if the number we're plugging in is a smaller value than negative 1, we're supposed to use the name of the function f of x, which is negative 3x plus 1. If the number is between negative 1 and 2, including negative 1 and 2, the function takes on the value 6, so it's always going to be 6 there. And if the value that we want to plug in is a number bigger than 2, then we have to use the function x plus 4 over x minus 1, rather than the other 2 that's provided. So in this case, we're again told to find each of the following limits or evaluating the limits. So we'll begin with the first problem. It's the limit as x approaches negative 1 minus with f of x. So they want me to plug in negative 1 minus, right? Remember the substitution method. They want me to plug in this number somewhere into the function. Now, the first thing I'm going to do is basically imagine a number line with negative infinity on one side and positive infinity on the other side. And I'm going to try to think about what is my x approaching. So if this is negative 1, where the heck is negative 1 minus? On which side of negative 1 am I coming from? Am I coming from the left side or the right side or what? And negative 1 minus is a number slightly smaller than negative 1. So I'm coming from the left side of negative 1. So since I'm coming from the left side of negative 1, the numbers I'm going to see there are things like negative 1.001 or negative 1.000527 or random things like this. The list goes on forever. So those numbers, what they have in common is they're all smaller than negative 1. They're all slightly smaller than negative 1. So the name of the function is negative 3x plus 1. So I'm going to take the limit as x approaches negative 1 minus and write down the name of the function, which in this case will be negative 3x plus 1. And again, as usual, we'll take this and punch it in there. So by direct substitution, this is going to be negative 3 times negative 1 minus plus 1. So removing the x and replacing it with negative 1 minus. Now, how do you evaluate this part of the problem? Negative 3 times negative 1 minus. In your head, just ignore the minus for a second. Just think like if I have negative 3 times negative 1, what would I do? Well, negative 3 times negative 1 will be positive 3. And that's it. I just write 3 plus 1, and the answer is 4. So not terribly difficult. It's just you have to be careful which side you're approaching from so that you can plug in the correct name for the function f of x. Okay, now looking at part 2 of the problem, we have the limit as x approaching -1 plus on the function f of x. So we want to find the limit as x approaches -1 plus. And so what name should I use? Should I put -3x plus 1 next? Should I put 6? Or should I put x plus 4 divided by x minus 1? Well, how do I determine that? Again, the idea is the same. I draw a number line, and you don't have to do that. You could do that in your head if you want. You can visualize it mentally. But for me, it helps to make the little graph and to think, okay, what does it mean to be -1 plus? -1 plus, that means I'm coming from the right side of -1. I'm slightly bigger than -1, so I'm over here somewhere. So what kind of numbers will I be seeing along the way? Well, I'll be seeing things like -0.999 or -0.9823 and so on and so forth. The list goes on forever. There's a lot of these numbers. So what they have all in common is that they are bigger than -1. And if I'm bigger than -1 but smaller than or equal to 2, the function takes on the value 6. It's always the same number there. It's always going to be 6. And so now I'm looking for the limit as x approaches -1 plus of 6. The key thing to remember here is that this is a limit of a constant. Doesn't matter what x is approaching. The limit of a constant is just that same constant itself, again, one more time. So the answer is basically 6, and we're finished with part 2 of this question. Now for part 3, what we're told is that they want the limit as x approaches -1 of the function f of x. So they want just the limit, regardless of direction, left or right, the limit as x approaches -1 of the function f of x. And here's how we do this. Since we already have the limit on the left and the limit on the right already evaluated, what we will do is we will look at these two numbers and we will ask ourselves, are they equal or are they not equal? If they are equal, then we write the answer down here and we're finished. In this case, though, the numbers that we got for the left and the right limits are not equal. So because they are not equal, what do I write down here? I write that this limit will not exist. The limit as x approaches -1 on this function f of x does not exist because the limit on the left and the limit on the right are not the same value. If they're the same value, then the function will have a limit and we write that number down. But in the case that we're dealing with, the limit on the left and the limit on the right are not the same. So what's actually happening on the graph is if you try to imagine what the graph looks like on the xy plane, you kind of have a line that goes sort of down and it stops at -1 here. Then you have a different line on the other side that goes from -1 to 2. And basically what this problem is demonstrating for us is that there's a jump between the two parts of the graph when x is approaching -1. So the bridges or the highways or whatever you want to think of it, like the freeways, are not meeting at the same location. There's a massive gap between the place where the left graph and the right graph are meeting. Therefore, there is no limit. Well, that happens sometimes. Oh well. So we're going to use the same function again multiple times below. And let's begin again by looking at what happens if x is approaching 2 minus. So first, I need to know what name to give the function in this particular part of the problem. So let's see, this is plus infinity, and this is negative infinity. This is 2 somewhere here. And 2 minus means that I'm coming towards 2, but I'm slightly smaller than 2. That's what the minus is for. Think of it like it's a little bit less than 2. Not -2, it's 2, but we're a little bit less. So the numbers I'm going to see here are numbers like 1.99 or 1.97351, and so on and so forth. These are the numbers that we are seeing as we get closer and closer to 2 from the left side of 2. And so what name should I give my function in this particular problem? Well, I am slightly smaller than 2. So the name is always the same. It's always 6. So I write down 6. And the limit of a constant, regardless of what x is approaching, the limit of 6 is straight up equal to 6. And that's the end of that part. So next, we will look at the limit on the other side of 2. So this is 2 plus of the function f of x. And so again, to help visualize what's going on, we will draw the number line representing all the numbers in the world. Here's 2, and this time I'm looking at the limit as x approaches 2 with the little plus sign on the exponent. That means I'm coming from the right side. That means the numbers I'm choosing are slightly bigger than 2. So these are like 2.01, 2.001, and so on. And so what is the name of the function when x is approaching 2 plus? So remember, these numbers, what they have in common is that they're all bigger than 2. And according to the theorem, or according to the function name, if the number I'm plugging in is bigger than 2, the name of the function is x plus 4 divided by x minus 1. So I write x plus 4 divided by x minus 1. And now it's just a matter of plugging, or direct substitution, plugging in the number 2 plus. So 2 plus plus 4, and then 2 plus minus 1. So wherever there used to be an x, we're going to remove it and write 2 plus. Now again, how the heck do you deal with this? How do you deal with 2 plus and plus 4? So just think to yourself, what is 2 plus 4? So just ignore that power for a second, and I get 6. So that's great. Nothing bad happened. I didn't get a 0, so we just move on with our life. And how about the denominator? Well, again, I'm going to start thinking, what is 2 minus 1? So again, ignore the power for a moment. And what would you get? You would get 2 minus 1, which is equal to 1. So, well, it's not 0, so that's great. The only time I have to worry is if it's a 0, then I'll have to be careful, is it 0 plus or is it 0 minus? Because the number could be positive if it's 0 plus, or it could be negative if the number is 0 minus. So I have to worry about putting a minus sign or not. But if it's a bigger number than 0, or if it's smaller than 0, strictly, like in this case 6 and 1, I don't have to worry about anything else. I just put 6 divided by 1, and the answer there is just simply 6, and that's it for that part. So great, the last part here is to find the limit with x, regardless of direction, approaching 2 of the function f of x. So how do I answer this problem? Well, again, we will look at these two parts and we will ask, are they equal or not equal? So in this case, both of them happen to be equal to each other. So what does that mean? That means that this answer down here will be identical. We will just write down 6, and we don't have to do any math whatsoever. We just write down 6 and we move on in our life, right? That's it. So the answers to the left and right are the same. So that means that the limit of the function exists and it's equal to 6. So in practice, what that means is that the graph of the function on the left side, where x is equal to 2, on the right side and the left side of 2 are basically meeting. So I don't know what the graph looks like. It could be this way, it could be that way, but who cares? It just tells me that the two graphs on the left and right side of 2 are meeting at the same location, and that location there has a height of whatever. In this case, it's apparently equal to 6. So I hope that made sense. If not, talk to me in office hours and let's figure it out. Okay, the last problem I have to worry about on this page is example 6, which tells me to evaluate the one-sided limit, and it's the limit as x approaches -2 plus of the problem, or the function, x plus 2 inside radical. So they want me to find out what this limit is equal to. And so again, the idea is we will try to use direct substitution if we can. If it doesn't work, then we'll think about what to do, what's alternative option, and worry about it later. And there's a second question here, which is a follow-up question, which is what's the domain of the function? So you know what? I would like to actually begin with that part first. Let's worry about the domain first and see if this is even worth investigating. Because if the domain doesn't even contain this number, then what's the point of doing the problem? So, we can save a little bit of time by answering the second question first before answering the first question about the limit. So let's talk about the domain of the function. So in this case, the function f of x that I'm seeing, it's given to me as the square root of x plus 2. Okay, and where did I get this from? I got it from basically looking after the limit. What's there? That's exactly what the function f of x is. Now we know that this function has a square root, so square roots are kind of picky because they don't like having negative numbers inside. The square root of a negative number, like the square root of -4, is not a real number. And so, yeah, even though it has an answer in the imaginary world or the complex world, we don't care about it in calculus. We will just pretend like it doesn't have a solution. So ideally, we don't want that to happen. We don't want the square root of a negative number. So that means what we want is we want to see a positive quantity inside of here, or maybe 0. It's valid to say square root of 0 because square root of 0 is 0. It is real. So it's okay to have 0, but it's not okay to have a negative value. So that means we want to have x plus 2 be bigger than or equal to 0. For the domain to exist, for the function to resolve itself, to give us an answer, we need to plug in a number that is, when added to, bigger than or equal to 0. So what's the number itself gotta be? Well, if we shift the 2 from the left to the right, we end up with x bigger than negative 2. So on the real number line, basically what this is saying is it's saying for your domain, you will have to pick numbers that are either negative 2 or bigger than negative 2. So this is kind of a review of what we did in the first chapter in this semester, but basically any of these numbers is a valid input for the function. If I plug any of those numbers in, then my function will be able to give me some results. So in this case, the domain written in interval notation will be negative 2 comma infinity. Or if you prefer interval notation, you can say that it's, sorry, if you prefer set builder notation, you can say it's x such that x is bigger than or equal to negative 2. Personally, I like this notation more than the set builder notation. It's a little bit faster, and since I already have the graph, all I have to do is just copy what's on the graph without the actual straight line, basically. All right, so that's the domain. So now let's see if we can investigate this part of the problem, the one-sided limit. So they're saying one-sided limit because the negative 2 has a little plus sign, so that means I'm coming from one side only. So we're looking now for the limit as x approaches negative 2 plus of the square root of x minus 2. So first, what I'm going to ask myself is this number, negative 2 plus, one of the valid inputs in my domain? Because if it is not, then I just say no solution and I just move on with my life. But if this number is part of the domain, then I actually have to do a little bit of work. And so let's think about it. What exactly is negative 2 plus? So negative 2 plus is something that is almost negative 2, but bigger than negative 2. It's basically this section of the number line. This is what we call negative 2 plus. Right? These are numbers like negative 1.999 or negative 1987 or negative 1.90521, whatever. It's not a single value. It's a bunch of numbers that are slightly bigger than negative 2. And so they are in my domain. So therefore, there is an answer to this question, and I have to find it. So, well, as usual, since x is approaching negative 2 plus, and we have a limit, we will just take the negative 2 plus and replace all the x's with that value. So by direct substitution, we remove the x and replace it with the given limit. So in this case, negative 2 plus. And I think I have a typo here. I think it should be square root of x plus 2 rather than x minus 2. Let me just verify real quick. Yes, there's an x plus 2 there. Okay, so now that we've done that, we need to think about what's going on inside the radical. So what's happening with these guys? What are they equal to? Well, again, the idea is I need to think negative 2 plus 2. And when I think negative 2 plus 2, so ignore the plus for a second in the power. If I ignore the plus for a second, I get 0. And it's tricky when you get 0 because sometimes it matters if you're coming from the left or from the right. So like, for example, if I'm putting square root of negative 0.0001, that's not real. But if I put square root of plus 0.0001, then that's a real answer. So in this case, I have to pause for a minute, and this think method does not work anymore. So I have to just basically try it out to myself. I know the answer is going to be 0 here because negative 2 plus is a number that we mentioned earlier It's like negative 1.999. And then if I add 2 to it, the result is going to stay positive because 2 is bigger than the number that I'm putting there that's negative. So in this case, I know the answer is going to be 0 plus, but I'm going to write 0 and just end it like that. I don't have to put 0 plus. I know the number is virtually 0. The only thing I have to be careful about is it 0 or is it not real? And in this case, it turns out that if I plug negative 2 plus and add to it 2, this is similar to doing something like negative 1.999 and adding 2 to it. And the answer is going to be like 0.000 whatever, so I'm just going to round it to 0. If I try it out again, negative 1.907 and then add 2 to it, the answer is almost 0, so I'm just going to round it down and say it's 0. So the list goes on forever, and we don't have time to go through every problem, but basically, the number you're plugging in is always smaller than the one you have on the side, which is 2. So the answer is always almost 0, but it's slightly more. So it's technically 0 plus, but we don't write the plus sign when we're writing the final answer. We just say simply 0. Okay, finally, we're in example 7, where we're told to find each limit analytically. So again, that just means try not to use tables or graphs to find a limit, but I would recommend that you try to graph the functions that we're finding limits for and confirming that the limits are what we're saying they are. So we'll start with the first one, where it says you're given a limit as x approaches 3 of the fraction x all divided by x minus 3 squared. And as usual, the first thing we're going to do is try to do the direct substitution method, where we plug in the number into all the x's. In this case, the number we're plugging in is 3 because that's what x is approaching. So I put 3 on the numerator and then 3 in the denominator where x is found, and I'm going to end up with 3 divided by 3 minus 3, which is 0, and 0 squared is going to be exactly equal to 0. And unfortunately, 3 over 0 is not defined. But I really have to be careful in this problem because I'm getting 0 on the denominator, but no 0 on the numerator. So there may be an answer, it's just that we have to be a little bit careful. So let's go back a few steps. We were told that x is approaching 3. So if x is approaching 3, where does it come from in this case? Does it come from the left or from the right? And the answer is actually both. It could come from the left side or it could come from the right side of 3. So let's analyze what happens from either side. If x comes from the left side of 3, the numbers I'm going to be seeing are things like 2.999 or 2.9872 or 2.9154 and so on and so forth. The list goes on forever. It's a massive, massive list. Now imagine you're taking one of these numbers and then you're subtracting 3 from it. What will the solution be? Well, I bet that your calculator is going to say something like 0.000, like a bunch of zeros and then maybe like a random number at the end. So what I'm trying to say is, if I take a number smaller than 3, slightly smaller than 3, and I subtract 3 from it, the answer is going to be something negative. So 0 minus. It's almost 0, but it's negative. How do I say it's almost 0, but it's negative? I write 0 minus. So for all of these sides, where x is coming towards 3 from the left, the value of the result is going to be 0 minus. Now, on the other hand, if x is approaching 3 from the right side of the graph, it's going to be coming across one of these values over here. And these values over here, what do they look like? These numbers over here on the side of 3, on the right side of 3, are things like 3.00001, or maybe 3.010101, or maybe 3.000254. And again, the list goes on forever. There's so many of these numbers that are close to 3, but slightly bigger than 3. And if I take any of these numbers and subtract 3 from it, so it's a number slightly bigger than 3, and I'm going to subtract 3 from it, what's the result going to be? Well, your calculator is going to say 0.00000 and then some random number at the end. So the answer is almost 0, but it's a positive quantity. Regardless of which number I take, The number is always going to be very close to 0, but it's almost 0. For all intents and purposes, we will call it 0, but it's on the positive side of 0. And so, again, the result is 0 plus. Now, does it matter which one of these it is? Well, not really, because regardless, everybody is going to get squared eventually. So whether you have a 0 minus or 0 plus, 0 minus or 0 plus, both will get squared, and the squaring will make it a 0, but it's going to be a positive regardless of what you started with. If you had started with a positive number, then great, the answer is going to stay positive. But if you start with a negative number, the answer is going to become positive because of the squaring. So in reality, this down here is not correct. I shouldn't be writing 0. I should be writing 0 plus and then squaring it. So this is the time when you have to be careful about those little powers, plus and minus. And again, regardless of whether it was 0 minus or 0 plus there, the result is going to be 0 plus eventually. So if I had started with a 0 minus and I squared it, it becomes 0 plus. If I had started with a 0 plus and I squared it, I'm going to end up with 0 plus. The bottom line is, this is not 3 divided by 0, so actually it's 3 divided by something super, super small. So you can give it a shot now. You can whip out your old calculator and divide 3 by 0.00000000001, for example, and see what the calculator does. Or change the 1 to maybe 125, or maybe change it to 197. Or get it as close as you want to 0 as you like. And what you'll notice is the numbers will get larger and larger. With every time you do this iteration, with every smaller number you take, the number that you get on the screen is going to be larger. So how do we say that mathematically? We say plus infinity here. And so the result is that we're getting a plus infinity, which means that the limit actually does not exist. So having an infinity at the end, it doesn't mean that you got an answer. It just means that you have no limit. The function that you're dealing with just keeps going higher and higher and higher the closer you are to 3. So the closer I am to 3 from the left or right, regardless, it doesn't matter. The graph on the y side is going to shoot up to the top of the page, basically, or to the top of the ceiling, or whatever you want to call it. So that's how we deal with these problems where we have a limit and we get an answer that is not 0 on the numerator, but it's a 0 on the denominator. So we have to be pausing, we have to be analyzing the situation a little bit more carefully. And we'll see that a couple more times down below in the next two parts. So this next one says the limit as x approaches 3 plus with x on top and x minus 3 on the denominator. So again, the idea is the same. I'm going to take my expression and I'm going to say x is approaching 3 plus. Let's remove the x's and replace them with 3 plus. So we do that for every time we see an x. We had one on the numerator and one on the denominator. Now, in this particular problem, there's a 3 plus on the numerator, so we could just write 3. It's not being added or subtracted to anything, so we could just ignore the plus and kind of round it off to say 3. But on the denominator, I have to be a lot more careful. On the denominator, I have a 3 plus and a negative 3. So let's see what we're dealing with here. So this is the real number line, which represents all the numbers in the universe from negative infinity to plus infinity. Here's the 3 that we care about. And now we are going to wonder, where is 3 plus? Well, turns out that 3 plus is slightly bigger than 3. So think 3.0001 or 3.0125 or whatever. It's a number to the right side of 3. That's why there's a little plus sign in the power. So it's bigger than 3 by just barely, by very little small amount. So, these are numbers like 0.001, 3.00000005, or the list goes on again. Now again, take one of these numbers and subtract 3 from them. What will your result be? Well, if you put one of these numbers into the calculator and do minus 3, your calculator is going to say 0 point blah, 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 a bunch of zeros, and then maybe like a 1 at the end, possibly. Maybe something else, but the bottom line is the result is going to be almost 0, but it's slightly positive. It's not negative, it's going to be slightly bigger than 0. That's because these numbers, which are the 3 pluses, are all bigger than 3. So That's why I'm going to write 0 plus on my denominator there. And so again, 3 divided by 0 is technically going to be for us infinity. We'll just write infinity to represent any number divided by 0. But in this case, both the 3 and the 0 are technically positive values, so we write plus infinity. Which again means that all this work was for nothing because the limit does not exist. Just because we got an infinity at the end doesn't mean anything. It just means that the graph of x divided by x minus 3 goes up forever as we get closer and closer to 3 from the right side. And so last one, we're dealing here with the limit as x approaches 3 minus. And again, it's the same expression just so we can see what the different scenarios look like. So as usual, x is approaching 3 minus, so I'm going to go ahead and plug it in into all the x's. This is the direct substitution method. So 3 minus, and then 3 minus, minus 3. So I'm putting the 3 minuses wherever x used to live. And again, on the numerator, we only have one single value. It's the 3 minus, so we'll just round it to 3. It's not being added or subtracted or multiplied by anything, so we'll just pretend like it's a 3 there. But on the denominator, I have to be, again, super careful because I know the result there is going to be almost 0, but am I on the left side of 0 or the right side of 0? Because 0 separates the negative things from the positive numbers. So I got to be careful to write down whether it's a 0 plus or maybe 0 minus, because that affects what kind of infinity over here. Is it plus or is it minus? So I have to be careful. I have to pause for a second and analyze this scenario again using my little number line. So a negative infinity on one side and plus infinity on the other side. And here's the 3. And where is 3 minus found on this number line? 3 minus is slightly smaller than 3. So think of numbers like 2.9999, or think of numbers like 2.98714, or think of numbers like 2.99999788123, and so on and so forth. The list goes on forever. It's a really, really big list. But regardless, take your own favorite number from that list, doesn't matter, and now subtract 3 from it. And you can do this with your calculator if you're having a hard time imagining it. But if I take, for example, the first one I chose and subtract 3 from it, my calculator is going to say negative 0.000001 at the end. So who cares, right? The bottom line is it's technically a 0 value. It's almost 0. But the result I saw on the screen was a negative amount. It's very, very small, but it's a negative amount. That's where the 0 minus comes from. And so I'll write it down on the denominator, 0 minus. And what do I get from doing 3 divided by 0 minus? So because it's not 0 over 0, I get infinity. And in this case, the 3 is positive, but the 0 is technically negative. So positive divided by negative sign is going to be eventually a negative solution. So negative infinity is what I'm getting. And again, regardless, the answer is the limit will not exist. DNE stands for does not exist, by the way. So all that work to finally see does not exist. But what's the meaning of all this? The meaning of all this is that as x approaches 3 from the left side, the graph of this function x divided by x minus 3 is going down forever. So the graph points towards the bottom of the page or towards the floor, however you want to think about it. That's what's going on. And what I would recommend for you to do right now is to use your graphing calculator, graph this function f of x, and look at what's happening around the x value 3. And you'll see that on one side it goes down forever, on the other side it goes up forever. And that's what we basically were able to confirm using these limits.